Second important parameter that's being measured with the GlycoCheck system, obviously, is the health of your glycocalyx. And the method that we employ in the GlycoCheck software is, again, that we look at many individual capillaries. So this is an example of one of those capillary segments. We measure hundreds of thousands of capillaries, how the red cells are flowing through these individual vessel segments. And we measure the width of that red cell column and see how close it can get to the endothelial surface. As I shown before, in a healthy individual, the red cells cannot get close to the endothelium because that space between the red cells and the endothelium is filled with that protective glycocalyx gel that prevents the red cells from getting too close to the endothelium. Again, schematically, that's shown in this slide. So in a healthy microvascular system, if we measure the position of the red cells, they stay pretty close to the center where they are flowing, and we measure the radial motion of the red cells, how close they can get to the endothelium, but they cannot get too close because they are bumping into that healthy protective glycocalyx. In contrast, patients with a compromised glycocalyx, the red cells just penetrate a little bit deeper. And so by measuring the depth of penetration of the red cells into glycocalyx, we have a functional parameter to describe the level of damage to your glycocalyx. This shows in a little bit more detail how we measure the depth of penetration of red cells into glycocalyx. So this represents one of those 100,000 vessel segments that we analyze. And the black line is the position of the endothelium. In each segment, we measure the width of the red cell column approximately 1,000 times. And based on the 1,000 width measurements of the red cell column, can define the median width of the red cell column as a measure for vessel size. And also we can measure the outer edge of the few red cells to try to get closer to the endothelium. So by measuring the outer edge of the red cell column, and by comparing that to the median width of most of the red cells in the red cell column, we can define what we call the perfused boundary region. So that's the interface region where some of the red cells try to move radially towards the endothelium. They bump into the surface of glycocalyx. So the dark blue part is the protective part of glycocalyx into which they cannot penetrate. And then the light blue part is the surface of glycocalyx into which some of the red cells can penetrate for a short distance. So in a healthy individual, the light blue part is relatively small, while in contrast, when you have a damaged glycocalyx, as shown on the right, again, the black line is the endothelium. The dark blue part is the protective part of glycocalyx. Now you can see that more red cells can penetrate deeper into the surface of glycocalyx when glycocalyx health is compromised. So by measuring how deep the red cells can penetrate in that light blue area, the surface area of glycocalyx, we can measure an increased depth of penetration, which gives you an increased dimension of that perfused boundary region, or PBR as we call it, as a measure for glycocalyx damage. Now, if we take that measure for glycocalyx damage, that PBR value, we can look in different patient groups to see what's the level of glycocalyx damage by using the GlycoCheck system. So this is one example of early changes in glycocalyx damage, comparing young healthy controls on the left, older healthy controls in the center, and early type 2 diabetics before they get organ complications on the right. So this shows the depth of penetration as a measure for glycocalyx damage. And we see that the depth of penetration increases by 1/10 or 2/10 of a micron, going from young healthy controls to older healthy controls to type 2 diabetics. So the 2/10 of a micron increase in penetration of red cells into glycocalyx is a little bit of damage already in this early stage. If you recollect the earlier presentation, glycocalyx typically has a dimension of about a micron in a healthy individual. So this early stage of challenge, they start losing 1/10 or 2/10 of a micron of their glycocalyx. Well, another example of damage to glycocalyx is shown in this cardiology study. This is comparing cardiology patients with large vessel disease and small vessel disease compared to age-matched controls. And again, this shows an increase in damage to their microvascular glycocalyx, but also their large vessel glycocalyx in these patient groups. Another example is shown here. This is a study with neurology patients. These were patients that were in the hospital because of a stroke. We made two subgroups of stroke patients based on their MRI images. So they take a picture of the brain with an MRI machine, and based on the MRI picture, you can either see that you have an individual with a stroke without so-called white matter lesions, without all little white spots in the brain showing little lesions in the brain, or patients that do show all these white matter lesion spots in the brain. And it's thought that these people with these white matter lesion spots in the brain get these little lesions because of a microvascular defect. And confirming that hypothesis, we show that if you compare the stroke individuals without white matter lesions in the brain with the ones that do have white matter lesions in the brain, that there is a significant increase in the level of damage to the glycocalyx in the microvasculature in the latter subgroup of neurology patients. But the biggest before that, one of the other studies that we did was in pregnant women. We know that with pregnancy, there's already a little bit of glycocalyx damage compared to non-pregnant women. But then again, within the pregnant women groups, we find individuals that have a normal pregnancy and normal levels of blood pressure, but the subgroup of pregnant women develop what's called early onset preeclampsia. So that's a complication of the pregnancy where the microvasculature will be damaged and people start losing fluids and proteins by leakage through the damaged microvasculature. And again, we show that people with preeclampsia, pregnant women with preeclampsia, show a significant increase in glycocalyx damage in the microvasculature. But the biggest levels of glycocalyx damage we find again in the ICU in people with sepsis or people with COVID-19, as we'll show you in a few more slides. So compared with young healthy controls, we see that critically ill patients in the ICU can have up to a micron more glycocalyx damage in the microvasculature. So the red cells can penetrate a micron deeper into glycocalyx, which actually means that most of their glycocalyx is completely damaged and destroyed. So the red cells get very close to the endothelium, and at some point they touch the endothelium and they start sticking to the endothelium, causing a lot of complications and loss of organ function and organ failure. So the ones with the biggest level of glycocalyx damage in the ICU are also the ones that get too many complications and organ failure and don't survive their stay in the ICU. As with the capillary density, we realized that if you measure that level of glycocalyx damage by measuring the depth of penetration red cells into glycocalyx, also that level of penetration is flow dependent. As shown in the middle graph, if you look at the apparent level of glycocalyx damage in different microvessels under different flow conditions, that in a healthy individual, if you look at low flow sites, where there's a low metabolic stress on glycocalyx, then the depth of penetration is lower at the low flow sites in healthy individuals. While in contrast, in patients with a compromised level of flow control, if you look at sites of low blood flow, those sites generally have a high metabolic demand and stress on glycocalyx. So we find more glycocalyx damage at low flow sites in patients. So if we take the flow dependency into account and extrapolate to the low flow regions, then we were able to make the differences in glycocalyx damage between healthy controls and patients much more significant and much more sensitive to identify damage, but taking the flow control and the flow dependency of glycocalyx into account. So if we combine the capillary density count, the recruitment capacity, the flow dependency of capillary density with the flow dependent estimate of glycocalyx damage, we can now define what the so-called Microvascular Health Score.